pipeline, but also in such a way that I'm not spilling time in the other stages. Then the pipeline should be well balanced, that in all stages I'm using plus or minus the complete time of the period. Now, if I put the effort in nicely designing the processor and I make a bad choice in here, I screw up the entire system. And then you see the decision on the cache will also depend on how this one is actually fitting with the clock period of the processor. And if I cannot do that kind of heat calculation in one cycle, I should better drop the solution. Now, there are other issues which are important, and this is block replacement. Whenever I have direct cache, there is no block replacement. Whenever I have associativity, starting with two-way going to full associativity, I have to find a way to select the victim. Which of the sets I should kick out in order to bring a new cache line. And I have those policies. I can flip a coin. I can ask somebody. I can use a FIFO kind of policy. I can use a least recent utilized policy. Most of the time we use the last one, which is assuming that whatever I did not need in the recent past, I most likely will not need in the close future. If I make here bad choices, I may kick out, I may evict information from the cache, which I may need just immediately later on, which is not good. Now, we are dealing with the situation when I'm looking for information. But the cache, it's actually a buffer between the processor and the main memory. In the same way I'm reading, I'm also writing. And now what I have to do is I have to write in such a way that I do not create mess in the system. Then one solution will be to write in the cache and not to update the location in the main memory. Then when I am changing the value of a certain location, of a certain variable, I'm just updating that value in the cache. This is good because the transaction will be short. It's one cycle. But it creates me a problem. In the main memory, I do not have a valid copy of that variable. Now, this will not be a problem as long as I'm operating with that variable and it is present in the cache. But will create problems when I do not have capacity in the cache and I have to evict that value, that line from the cache. Because now that eviction will require a write in the main memory. It's not only that I'm dropping that line, I have to update that location in such a way that in the main memory I have now a coherent image of the evolution of my program. Which means that if I go for that solution, a cache miss will result in a potentially write into the main memory. Then even more penalty in the cache miss. Then I'm missing a line, I'm missing a location that I'm looking for, which means I have to bring it from the main memory. And in the same time, I have to update a location which I changed. Then I have to do a read and a write, which is not exactly a nice situation. However, there are also pluses on this. Let's say I'm operating on a variable and I'm operating in a program a number of times, and I will do more updates on this variable. All of them will be done in the cache, and only at the end, when I'm kicking out the variable from the cache, I will do a write in the main memory. I have also another possibility, which is to write in both locations, in the cache and in the main memory whenever I do a write. Then I'm issuing a write, one cycle to the cache, and also I'm updating the main memory.
So
now,
doesn't it slow your CPU when you're going straight for the main memory? Because you have
it may or may not, depends how I deal with it. If I wait for that to complete, it will slow. It's not nice. But what we usually do if we go for that, we use a buffer. I put the information in the right buffer, and somebody else will take care for this update. Now, each solution has pluses and minuses. If I think from the point of view of the energy, write through is not exactly a good solution, because I'm spending energy updating a variable in the main memory when most likely will not be needed. Then, as I said, I'm working and I'm changing that variable 10 times, and I will do 10 writes which are not really needed, because when I finish and I take it out, I will do the write. The other one will create more complexity when I am having a miss. And depending on what I'm doing, I may go for one or another. Okay. And what we do is, most of the time, we go for write through if we don't really care for energy. Because if we design an embedded system where energy is very important, this might not be the solution. But desktop computers, they rely on this write-through policy. And the processor is not waiting for this write to complete. Then I put the information in the write buffer, and somebody else, a controller, will take care, the cache controller, that the information in the write buffer will be stored in the DRAM. And if the frequency of stores that I'm doing in the write buffer is not very high, the chance that the write buffer is full, it's not high either. This also depends on the speed of the main memory, which is DRAM memory. If that is slow, I may experience, full write buffers. And then I really stall, because there is no way to dump this to the write buffer. Yes?
You said that the writing to the or reading from the main memory that it takes a few hundred cycles.
Yes?
Is that largely latency or truly speed?
Depends on how your memory is designed. But if you have banks, might be throughput. If your memory is not organized in banks and is not pipelined, then it's latency. You have to remember that the access time for a DRAM, it's a lot larger, and also you communicate with the DRAM on a bus, while the cache, it's tightly coupled to the processor, to the CPU. The main memory is connected to another bus where other clients are also connected. Then in order to get a transaction, I have to get the mastership of the bus, I have to do the bus transaction, and depending on how that is organized, it may take longer or shorter. Then I may also have a direct memory access kind of engine, which may also be a bus master, and I may interfere with that too.
So a read plus a write is...
Sorry?
So a read plus a write is worse than just a read?
For sure. Except if I have a memory with 2 ports. Then if I have a memory with 2 ports, and I may have a port for read and a port for write, I can do them in parallel. But everything is coming with a cost. And the cost is, I'm not talking about area, I'm talking about time. A single ported memory and a dual ported memory will behave different in time. Then the dual ported is most of the time slower. and the dual port, it will also burn more energy. Now, depending whether or not I'm blowing the cycle time, I may or may not accept this kind of tricks. Because what you have to do is you have to make the choice which at the end of the day is giving you benefit. Then the fact that I'm doing things in parallel is very nice. But if I'm increasing the clock frequency, all the other customers in the system will suffer from that. And then instead of making the system better, I may make it worse.
Can I ask a question again? So with the right buffer,
Yes.
still it doesn't make sense to me,
Why?
because if it's 100 times slower, yeah, the DRAM, you could have every other line of code you use would be right, and then your buffer would be full. So you need a buffer that's bigger than your register file.
If that happens, that's your nightmare as a designer. But this is not happening because while you execute the program, statistically speaking, the chance that you will have to evict lines which were changed each and every cycle, it's 0.
Okay, but still, if it's 100 times, you'd need something that's bigger than your register file, and doesn't make sense, you know? It's
Modern processor work with, I think, 4 entries in the buffer very well. You are correct in the sense that, theoretically speaking, I may get up in such a problem. But in practice, due to the way programs are executing, I'm not evicted lines which were changed that often. And then I can put them in the buffer. Now, what can I do? If my programs are not behaving well, I will increase the buffer. And if it is a general purpose processor, I have to do an analysis on benchmarks and to see how they behave. But I think most of those modern processors, they have around 4 items in the right buffer. But in pathological cases, this may not work. Okay. You see, this is a design of cache. It's a two-way associative cache. This is from an alpha processor with the right buffer. It's just a beautiful picture, but there is not too much that I can tell you about that picture. But you should like it, right? Some maxes, some comparators. Okay, now we understand how the cache is working, hopefully. I worked an hour on that, then my yield should be high. I should assume that 99.99% of you do understand the cache functionality. Is that a correct assumption? Nobody wants to declare I'm the 0.01, right? Then I can say asymptotically 0. Okay, now, the point is, how do I evaluate the performance of this memory system? Because sometime an access will cost me 1 cycle, other times an access will cost me a lot more. And the way we evaluate the performance is by looking at what is called the average memory access time. When I speak about average, I already know the system is unpredictable. Then when I deal with real-time systems, I already have a problem. Because due to the unpredictability, I have to do things different in order to guarantee deadlines. If I have to complete a task before a certain deadline, and I have such a cache, I might complete it 99% of the cases. And if that is a landing system for an airplane, this might not be exactly a nice design, okay? And that's the reason why in most embedded systems where we have real-time things, we rely on scratch pads, which are predictable, but they have other kind of related issues. Now, then the average is given by the hit time plus the miss rate multiplied with the miss penalty. Then, whenever I have a hit, the access is the one cycle, or 2 cycles depending on how I'm designing it, or K, whatever. But most of the time, the hit time is 1 cycle. Probabilistically speaking, I can determine the miss rate of a cache depending on the capacity. And I can determine that by experiments or by other things. And I also know the miss penalty, because the miss penalty actually means that I have to wait until the item is brought from the main memory into the cache, and then I can use it. Then we start with a probabilistic game. Now we assume that things are in order. If I go for out of order, things are getting a bit more complicated, because now accesses may overlap. But let us look on the simple side first. Then this will tell me something about the performance, and what I would love ideally is that the average time is equal with the hit time. That's a good system. If I have a small miss rate or a small miss penalty, my average is getting close to the hit time access. Now, small miss rate means, first of all, large capacity. The larger the cache, the smaller the chance that I'll miss, right? Now, let us look on how we can improve the performance of the cache. And we can look at each of those 3 parameters. And we'll start with the miss rate, because the miss rate is actually the weighting factor which is bringing into the picture the delay of the large memory. If I can make the miss rate low, the miss penalty can be high and will not be that much visible. Then it's very important that I improve the miss rate, which means if I can use an oracle, I will always have the information that I'm looking for. I cannot use an oracle, but I can try to improve the efficiency of this system. And now, in order to understand how to improve that, I have to understand when do I get a miss. And we have what is called the 3 C's, from cache, misses, and also all of them are called with C. It's compulsory, capacity, and conflict. Forget for the time being on the last one, which is good for, I only see that in multiprocessor whenever I have coherent story. I kind of told you about that. Then I have compulsory misses. Whenever I'm looking for the first time for a location, when I start the program, there is no way that that information is in the cache. And that kind of miss I cannot avoid. When I'm looking for the location on the first position in the cache line, it's not there. Cannot be there because I just started. And those misses, are part of my life. I have the capacity issue whenever I cannot have enough location storage in order to memorize all the lines that I need for the execution. While I'm executing, I need to have, a certain number of lines in the memory in order not to experience stalls. If my memory is not large enough, I cannot accommodate that. And the other one is conflict. When several blocks map in the same location, I have a conflict even though I might have capacity. This is mostly true for direct map caches, where when I have a conflict, the rest of the cache can be empty, but I still have to evict things. Okay, now let us look on a beautiful diagram, which is not a pile diagram, you know, but computer architects like those too. What do I see here? I see different cache sizes, and with different colors, I see different types of misses. I see that compulsory, there is a missing letter there, are actually negligible. And they are there all the time. Then I see that the green one is the capacity. As expected, the higher the cache, the lower the contribution of the capacity misses in the number of misses, you know. I see when I have a very small cache, a lot of the misses are coming from there. When my cache is large, very few of them are from there because I have enough room. Now, in the top of this compulsory and capacity, I may have more or less misses from the conflict depending on the associativity. You see, if I have an 8-way associativity, like I only add the blue, then I have capacity, then if I decide for a certain design, let's say no, for let's say 16 kilobytes, this is something that I cannot avoid, and that's my biggest problem. And the conflict is actually very little. And frankly speaking, if I have enough capacity, the conflicts are very low as long as I have at least 2-way associativity. You see that if I have a direct map cache, I still have things coming from conflicts because there is no freedom in replacement. But if the cache is large and I have at least 2 ways, the conflicts are kind of disappearing. Now, when I'm reducing the cache size, the influence of this associativity is actually getting larger. Looking at this diagram, or at such a diagram, I can make a decision which type of cache I want to use. Because it may make no sense to make it larger than a certain value. Now, this is looking in a slightly different way at the same problem. I have the dimension of the cache and the proportion of the misses which are coming from capacity, from compulsory, and from the lack of associativity. And we see that the big problem is capacity. Then if I don't have enough capacity, I'm not doing good. And then it's good to have some associativity because direct mapped has problems with conflict. At least 2-way will solve some of those conflicts. Then if I have a reasonable dimension and at least 2-way associativity, I'm kind of in business. Now, when we talk about a cache, there is another parameter that we did not discuss explicitly in performance. And this one is the capacity of the cache line. I was saying that I have a cache line which can store 4 elements, but it can be longer or shorter. In here, we have something which analyzes the block size and the miss rate corresponding to that for different cache capacities. Then I may have small blocks, then this is the cache line with 16 bytes, or I may have very long blocks. Now what we see is that whenever the cache is large, the dimension of the block does not really have an influence on the miss rate. You see those curves are very flat. Okay? Now when the cache is small, the dimension of the block do have an influence on what's going on. If I have a small cache and a large block, it means that I do not have a lot of sets. and because I do not have enough sets, the conflict misses are increasing. Also, when I have small blocks, I'm increasing the number of compulsory missing because I'm getting one block which is small. Next time I'm getting another block which is small. Then the number of blocks for the same capacity, whenever are small, is large, then the number of compulsory misses is increasing. Then what I learned from this diagram, just a sec, is that when the cache is big, the dimension of the cache line will depend on other things but the misses. Will depend on how I'm doing the transactions with the main memory. Will depend on issues like how much area I'm willing to spend, how much energy I'm willing to spend. When I have a small cache, I have to be sure that I'm choosing a well-balanced dimension for the block. Like in here, you see, I should better be somewhere here. And if I deal with 1 kilo cache, I better go for 32 or 64 block. If it's smaller, I'm increasing this. If it's higher, I'm increasing this. Yes?
Well, you answered the question.
Then I answered already. You see, this is called prediction. Or maybe you were too fast in thinking, and then you did look ahead.
It's not a problem.
No, you did look ahead. Then you were running faster than me. Huh? Okay. Now, okay, we kind of discussed that. Okay. Then what we saw is that increased associativity is actually good. And if we look at this diagram, we see this kind of interesting rule of thumb is that you can play capacity with associativity. Then if you have, for example, an 8 kilobyte budget for the cache, you can use it like 8 kilobyte with one way or like 8 kilobyte with two way. Plus or minus, it will give you the same performance. Okay, this is what I can read in this diagram. This is 8 kilobyte. One way is this capacity, and two way is kind of this rate. Okay, it's an approximation. Then most of the time, what I see is that the budget will count the most. Now, this is an approximation, and in reality, if I'm spending this budget in associative memory, I'll do slightly better. But there is something which I said, and I skipped from the previous slide, is the implication on the clock cycle. Associativity will require to do more things in parallel, and sometimes I have slack in the clock period to hide extra overhead. Other time I do not, and then if I'm blowing the cycle time, I'm degrading the entire performance of the processor. Then I should, in principle, go for associativity, except when I have consequences which will affect all the other parts of the processor. In that case, I have to think twice. Okay. Now, we see that there is a problem with associativity because we have to do comparisons in parallel, and as I said, sometimes this cannot be accommodated in the clock period. What we can do is whatever we know already from computer architecture, which is called prediction. You see, the tool set of a computer architect is very limited. We have a couple of ideas and we apply them in very different concepts. We don't have a lot of ideas. One of the basic things is prediction, right? And then we say, I have a problem, let's predict. Now I have 4 sets. In the same way I use some kind of bits in order to do branch prediction, I can also use some bits and say, I'm looking for this address. Last time it was in set 1. Most likely will be in set 1 also now. Then, based on those bits, I'm looking in set 1. If I'm there and my prediction is good, my, let's say, 4-way associative cache will behave like a direct map cache with a small cycle, very fast, still associative. If I'm wrong, I will spend an extra cycle in order to determine where else is the information. I may spend 1 or 2 cycles depending on how I design. If I'm through most, as usual, if I'm correct in my predictions, this penalty will be small. And then I will have an associative cache with the benefits of the way associative cache behaving most of the time like a direct map cache. That's the idea of prediction. If I do prediction right, I have it with one comparison. Low energy also. I'm just activating one set. I'm fast. Guys, you are not working any longer. What happened? I had a better view when you had your laptops open. Right? Now I can see your full picture. I noticed that long time ago, but I make some intermezzos only from time to time, just to cheer you up. The class has to be fun. We had a physics professor which was speaking very flat. I don't know if you know the Orthodox chants in the church. He was speaking it that way. It was very boring and we are all having headaches after the class. He was never stopping, never making a joke or other kind of things. And I really disliked that. And that's the reason why I think it's good from time to time to have a chat with you, which assumes it should be bidirectional. The problem is you do not appreciate that. Then each time when I finish the class, I'm frustrated. I go in my office and I say, next time we have to talk. And I know we'll eventually have to talk, but in different conditions. And I'm pretty sure you will not like that talk. Because now there are no implications on the talk. You just get trained to talk with me. In the exam or in other discussions, you have the stress. Okay, now, if I'm not correct, I will have to do 3 more comparisons in parallel, then invest more energy and an extra cycle and see if I have a hit or not. Then my system will have different kind of consumption, energy-wise and time-wise for hit, based on this prediction. Okay, now we are essentially talking about what the hardware can do. But there are also many things which the programmer can do. Now, these days, programmer is not doing much. The compiler is doing a lot. In old days, we are also programming in assembly, and we are thinking about the implication of each and every instruction for the processor, how to optimize things. Those are long gone. But the compiler can do things in order to help the cache. And what can the compiler do is to restructure the program in such a way that the number of misses are minimized. Then you play with loops, you play with data layout in the memory, and only the sky is the limit on this one. And there are wonders which can be done by the compiler. And you see, we can do things on the instructions. and we can do things on the data. In modern processors, most of the time the caches for instructions and for data are different. Do you have an idea why? Hmm? Yeah, but why do I need different caches?
Maybe it's easier to loop over data if you don't have the instructions.
Okay, then I'm creating parallelism. Then if I have two caches, I can look in both of them in the same time. Now, if I look at a pipeline in a processor, I have instruction fetch and decode, and I have execute. Instruction fetch and decode will require instructions, and execute will require operands. If each of those is in a different place, I can do those in parallel. But it's not only that. The cache, it's making an image of the behavior of the program. I'm bringing things which I need, and based on the locality, they should be there. And there are different kind of behaviors for instruction and data. When I'm processing data, I want to have the data not interfering with the instructions. And I think all modern processors do have a data cache and an instruction cache for that reason. Okay, now you can merge arrays. You see, I am working from the programmer point of view. This one will do no pain. You as a programmer can write first or the second. The first one, it's a bit more logical because you separate the variables as they are in the algorithm. It's array A and array B. Because you process them in the same way, and they be located in different places in the memory, your cache will not behave nicely if that's done. But if you pack them in one structure, and they are located in a consecutive area of the memory, then array A element I, array B element I plus 1, I plus 1, okay? When I'm processing them, they are consecutive, and I will diminish the number of misses. And this is not costing me anything. I mean, you will not suffer any pain when you write like that. It's just the fact that you have to think about. Now, modern compilers can do that for you. But not all the time, and not always it's obvious for the compiler that things can be done. Now, essentially, this is more important for the embedded systems crowd. Then if you are an embedded system student, try to remember this. Whenever you will be, working in a company, your boss will be very happy if you play that kind of tricks and you improve the performance by 50% just with doing a more careful programming. You can also play with loops. You see, I have loops, and which are operating on memories, on arrays. Actually, those are matrices. And depending on how the matrix is stored in the memory, which can be row-wise or column-wise, might be good to change the loop one way or another. You see that in the first loop, I'm actually doing what is called the stride addressing. Then I'm addressing location 0, location 100, 200, whatever, because my matrix is stored row-wise. And I am processing it column-wise. Now what I can do is I can interchange the loops, and then I'm doing, the right processing for the matrix. I'm processing it as it is stored. Again, that kind of things we do not care about most of the time. And the way you store the matrix in the memory is very important. In some kind of application, you do the storage block-wise. If you do MPEG decoding, you remember that you deal with blocks, macro blocks, sub-blocks. Sounds familiar? Non, jamais couché avec. No? You never heard about MPEG? Come on, you are listening music. MPEG.
Yeah.
Okay, the decoding of the MPEG, it's actually done on matrices which are 8 by 8 elements. In order to do that efficient, instead of storing the matrix, let's say, completely row-wise, I'm actually storing block after block. Then I take a block, next block, and they are sequential in the memory. And this can help me in performance. How come that you don't know about MPEG? I'm surprised. Then you use technology that you don't understand? Why if it is malicious? What if the music is actually embedding some signals which are manipulating your brain? Don't laugh. This is possible. This is manipulation which is done by video clips, things that you don't see but you see. In the same way you may have in music. Okay, this is about blocking. It's exactly what I told you. Then I'm storing now in different ways. I can also do loop fusion. You see, I had 2 loops, and instead of 2 loops, I'm just doing the fusion of them. I'm doing the same calculation, but inside the loop, it's more calculation. And I'm addressing the involved matrices in only once, and I'm doing a better job. And what you see is that compiler optimization can pay a lot, depending on what I'm doing, what kind of techniques, and what kind of application I'm doing. You know, some applications are not very sensitive to that, but in other applications, this may help a lot. Now, I have to stop here, unfortunately. Tomorrow we'll continue the story.